All right. We generally start about 5 minutes after 5 to 10 minutes after the hour. Okay.
Mm-hmm.
Get the program running then. Yeah. So, yeah.
Anyway, everybody's super nice here, so this is good. At the university, at the working place, is really everybody's super nice. So I'm happy. Until now, I'm happy that I moved.
Well, do you have your 1 gigahertz magnet now?
Yes. Yes, I have 1 gigahertz is on field. That's gone on field 8 days ago on a Friday, on a Saturday, no, 10 days ago. And and there is a 900 and there is an 800.
So you have a really nice array of spectrometers. Then.
Yes. Yes,
Yeah.
yes.
Mhm.
Yes. It is, and it's probably also much better sustainable than in Germany, because this is a national facility. So probably the investments will continue in NMR.
Well, you just need to get a Jaron for 1 or more of them, right?
Yeah, with these little things, the problem is not buying it. The problem is maintaining it.
Well, it's not. They're not. The Jartrons have been pretty reliable. Okay. They last for about, once you get one from CPI, they last about 10 years.
Mm.
And then, I think the only person who's had a significant problem so far is Gail, the PAP, and so the way they break the failure mode is a water leak. So you have to cool the collector and cool the cavity. And if the water isn't clean, it corrodes the cavity and systems. And so you get a water leak. Okay? And that happened to Gail, but they repaired it pretty quickly for him. So I don't think it's, they've been pretty reliable, really.
But running costs are high, right?
Well, for the gyrotron itself, it's not, but for the nitrogen to cool the systems, it's more expensive, yeah. So we need to, what we've developed we have a nitrogen generator. So we take air and separate it. So you take 3 liters of air and you get a liter of nitrogen and 2 liters of oxygen enriched air. And that cut the cost down dramatically. That's the way we run our 700. Right? Now we still have, so the machine Michael's working on, the 140 still runs off boil off. So we run off boil off sometimes, but a lot of the time we run off this separated nitrogen. So it cuts it down by about a factor of 4. And Xander Barnes has made some further improvements in the heat exchange system. So there's been, it's improved over what it was initially. Yeah. Quite a lot. Yeah. So,
yeah, maybe something to think about.
Well, yeah.
Is there a gyrotron in the UK at all?
There's one in Nottingham at 600. Yeah.
Okay.
But, the future of DNP is spinning fast. Well, one view of the future of DNP, I should say, my view, is spinning fast, at 40 kilohertz or higher, and at high fields, because it turns out at low temperatures, a lot of the broadening is homogeneous in nature, and the way you get rid of that, get the resolution back, is to go to high fields, separate the shifts, and to spin fast and probably decouple more robustly. So we have a paper coming out in PNAS on a beta, in which we did with Anne Lesage. She had the only 1.3 millimeter rotor system, and the resolution is comparable. The resolution in A beta samples is comparable, identical to what you get at room temperature. So,
wow.
And then you get a factor of 20 or so. In this, we got a factor of 20 enhancement, but that'll improve. That's improved already since we did the experiments. Yeah. So it's actually about a factor of 6 more higher sensitivity than protons. That's an estimate in proton detection.
Sounds great.
Yeah.
Sounds really great.
Okay, so we're at 5 minutes right now. Okay. Maybe we should get started. Okay, so welcome everyone to the solid state NMR DNP ZOOMinar. Kong, you want to give your routine?
I'll speak for 1 minute.
Go ahead and give your routine.
Yeah, as I promised, I will only speak for 1 minute or even less. So like as usual, if this is your first time here, or if you are not very familiar with how we run this system, feel free to sign up for our mailing list, of which the address I just put in the chat room. And then if you are interested in listening to the to what have been presented in the past section, feel free to go to the website, in which we usually keep a recording on YouTube of the speakers who had given us their consent. And in the very end, we still have a Dropbox to keep some of the questions that we'll answer. So Bob, would you like to introduce our speakers?
Okay,
today?
so today we have 2 really excellent speakers, Teresa Carlomagno from Birmingham and Hannover, maybe somewhere in between. And then also Daniel Jardon-Alvarez, who is presently a postdoc with Mikhail Leskis at the Weizmann Institute. And Teresa has a very long history, very impressive history in magnetic resonance. She got her PhD in Naples and then was a postdoc, I guess, at Scripps first, and then went to the
Other way around.
Other way around. Okay.
First Christian, then Scripps.
Okay, went to Göttingen first, and then to Scripps, and then she was on the staff at the EMBL lab in Heidelberg, I guess, and then took a position after that at Hannover, and quite recently, I think last week, sometime very recently, she moved from Hannover to Birmingham, where she is in charge of the National NMR facility in the UK. And she's done a lot of really interesting science in her career. And today she's going to tell us about some of her recent solid state experiments, magic angle spinning on RNA. Okay, so Teresa. Yeah.
Thank you, Bob, for the very nice introduction. So let me start with a disclaimer. I am not a solid state NMR spectroscopist, but a solution state NMR spectroscopist. So be kind to me in the questions, and if I say something that is not, let's say, well, I hope I say only correct things, but otherwise be understanding to me. So as Bob said, I recently moved on 1st of October to the University of Birmingham, where I'm part of the School of Bioscience, and also head of the Henry Wellcome building. This is an NMR center that provides measurement time to the entire UK with the 1 gigahertz, 900 and 800 high field spectrometers, in addition to 3600s and 2500s. But the research that I'm talking to you about was done in first at the MBL, where we started moving into solid state NMR spectroscopy, and then continued at the University of Hannover, where I've been for the past 6 years. So first of all, let me give you a reason why a solution state NMR spectroscopist would want to move to solid state. So what we are interested in doing is to understand how large protein and protein RNA complexes work, and in particular to understand how they work in the presence of dynamics. And I'm not talking about dynamics in the sense of moving of side chains. I'm really talking about dynamics in the sense of moving of entire domains, the docking of domains, releasing of products, for example, in an enzymatic context, and so on and so forth. And as I said, we study both protein-protein complexes, nucleic acids protein complexes, and protein small molecule complexes. In particular, we are interested in understanding how small molecules, for example, regulate the dynamic behavior of enzymes. And because these complexes that we study are quite large, as you see here, a couple of examples. This is 100 kilodalton in size. This is 400 kilodalton in size. We cannot apply like standard solution state NMR spectroscopy methods. What we have been establishing are integrative structural biology protocols where we try to integrate a series of techniques and of data that come from these different techniques in a non-crystalline environment, and interpret those data in terms of either one structure or of multiple structures. And an idea of the different techniques that we use or that we aim to use is depicted here. So, of course, we use solution state NMR spectroscopy, mostly looking at methyl groups of proteins, as Louis Kay has shown us that the methyl groups of proteins are still visible for complexes of several hundreds of kilodalton. And with these methyl groups, we apply extensively paramagnetic enhancement techniques to measure the distances between subunits in the complex. We have also applied the EPR techniques. We apply extensively small angle scattering, and in particular small angle neutron scattering in contrast matching. We have applied in the past FRET. We aim at also applying quantitative mass spectrometry data on interaction interfaces, for example, tritium exchange, or mass spectrometry cross-linking data. So with all of these, let's say, techniques together, we then develop methods that are able to somehow accept all of this variety of data and then put them all together and give the structure of the complex. And here is, for example, so this is an example of what we do. So we would start from the high resolution structure of single subunits of this complex, and the high resolution structure could be obtained by X-ray crystallography, by NMR, or by whatever other technique you would like to use. And then we put the different subunits of the complex together under the guidance of our NMR data in solution, which are mostly obtained through the observation of the methyl groups resonances and the measurement of paramagnetic relaxation enhancement effects by adding a tag on one of the subunits and looking at the effect of these tags on the methyl group of another subunit. And then we combine this NMR data with small angle neutron scattering data acquired in contrast matching, which give us information on the relative positions of subunits with respect to each other. And I don't know whether you are familiar with small angle neutron scattering and contrast matching, but what you can do here is to highlight only some of the subunits of a complex by deuterating them and using a solvent, a mixture of water and deuterated water, which basically mask the scattering of the wild-type subunits or the protonated subunits, and would only highlight the deuterated subunits. So for example, in this complex, if you use everything deuterated and only ASF1 protonated, you would see this part of the complex. And when you repeat this trick for a lot of combinations, you have enough data to basically restrict the position of these subunits. And this is actually a quite powerful technique that has led to the first structure of the ribosome in the early 70s. And at least in terms of positioning the different subunits, the people who used SANS in the early 70s they did get the structure of the ribosome correctly, as it was shown then afterwards with the crystal structures. However, all this nice scheme here works very well for proteins, because we can look at the methyl groups of proteins in solution, and we have now demonstrated it on different complexes, but it does not work too well on RNA. And this is because RNA does not have methyl groups, and for this reason it is difficult to obtain a solution spectrum of an RNA that is, let's say, larger than 100 nucleotides. And if you imagine an RNA which is smaller than 100 nucleotides but is inserted in the context of a large complex, then you can imagine that even if we can obtain a structure of the complex by knowing the position of the proteins with respect to each other, we will never be able to get to the atomic details of the structure of the RNA. So for this reason, we thought, why not applying a solid-state NMR on RNA protein complexes to obtain high-resolution structural information on RNA for complexes that do not crystallize. So they are not amenable to structural studies by X-ray crystallography, but they are also too large to be amenable to structural studies of RNA in solution NMR. So for this reason, being solution state NMR spectroscopy, we started to get interested in solid state NMR spectroscopy, and learned to appreciate the beauties of it. So our goal is really to develop methods that would give us the assignment and then the structure of RNA in solid state, and then develop these technologies to be applicable also to large protein RNA complexes. And of course, we needed to start from somewhere, so we took a complex that is not that big, but we know very well in the lab, and this is a complex of a so-called boxy-D RNA, which is depicted here in blue. It's a 26 nucleotides long RNA bound to a protein which is called L7A. And you may not be familiar with the structure of the RNA, but what you see here are two stems, one here and one here, that are connected by a region that forms a sharp kink, so that these two stems are basically form a structure that looks like this. And this structure is induced by the protein L7A. So there are two reasons why at this point we decided to go for a protein RNA complex and not for a naked RNA. The first reason is that most of the RNAs that we study are in complex with proteins, so we are also interested in developing methodologies that give us the distances between proteins and RNA. But maybe the most important reason is that we wanted to have an RNA with a well-defined structure. So we had tried before, when I was at the Max Planck in Göttingen, in a collaboration to get solid-state NMR spectra of a naked RNA. This was at the time the TAR HIV RNA. But so the HIV TAR RNA, but the spectral quality was really poor. So we did not put too much effort in the, let's say, in the sample preparation at that time. But you have to think that RNA structure is much more malleable than the structure of proteins, and what we could see there is that by taking an RNA which has a good structure at 25 degrees and precipitating it, you actually precipitate a mixture of structures with not so much local orders. So in this, for this study, in order to obtain an RNA with a certain well-defined structure, we decided to use this RNA in complex with a protein. And so what we have in rotor is not a crystal. So this complex actually doesn't crystallize. And if you look at the precipitate that we obtain in the microscope, you would see maybe a hint of some well-defined, let's say, sides of these precipitates, but actually nothing that to a crystallographer would look like a crystal. So then our first task was, of course, to look at the spectra of this RNA and assign the NMR resonances. And we started with acquisition of, with heteronuclear acquisition, so with acquisition of carbon and nitrogen NMR signals. And one of the characteristics of the RNA, both in solution and also in solid state, is that its spectra are really very much overlapped. So when we acquired the PDSD spectrum of this RNA, we realized that even though the RNA is only 26 nucleotides, we had too much overlap, for example, in the sugar region. And this is a very common situation that we see also in solution state NMR, because when you go away from the C1 prime, so the C2 prime, C3 prime, C4 prime, and C5 prime NMR peaks are pretty much degenerate, and the spectrum is full of overlapping peaks. So we decided to go with single type nucleotide labeling. So we generated the complex that I've shown you before with only A's, for example, carbon 13 and 59 labeled, or only U's, or only G's, or only C's. And in order to obtain the intranucleotide assignment, we ran experiments which are reminiscent of the experiment that you would run in solution state NMR. So namely, we first looked for the correlation between the C8 and C1 prime atoms with a common nitrogen. So, and in this way, you get the correlation between the ribose spin system and the base spin system, and you can assign the resonances to individual nucleotides. And here what you see is a two-dimensional Tidal PDSD that we ran on this sample. And as you see, the resonances are, so the peaks are quite nice, and you can recognize all of the A's contained in this sample, with the exception of these two here, which are probably in many different conformations, and we were never able to see those in any of our sample preparations. So we then We then went to the sequential assignment, and for that, of course, we needed to use combinations of single type nucleotide labeling. So we used, for example, samples that are labeled in the C and in the Gs, or in the A and Gs, A and Cs, and so on and so forth. And with a combination of all these samples and all these experiments, we were able to obtain the complete assignment of the resonances of this RNA, and also enough structural restraints. So what we used for the assignment are mostly 2D Tidal PDST experiments with a shorter or longer PDST mixing time. And what we used as structural restraints are NHHC and NHHN type of experiments where we use the proton spin diffusion to correlate the two heteronuclei, and from the intensity of the peak you can estimate a distance. And we also use nitrogen RFDR experiments to detect the base pairs. And here I show you an example of the experiments that we ran to assign to have the internucleotide assigned, so the sequential assignment of the RNA. And as you see, the peaks that are obtained for so between carbons that are on different nucleotides, and which are here indicated in red, have a quite small intensity with respect to the intranucleotide peaks. And this was on a 600 megahertz spectrometer, and at about 10 kilohertz, 10 to 12 kilohertz of spinning frequency. And as you see here, there is not very much, let's say, intensity to lose here, because these peaks are already quite, I mean, they are there, they are clearly there, they are clearly above the noise, but they are not extremely intense. However, we did our homework. We could assign the RNA, we could measure the distances, and what we had in the end is the first structure of an RNA solved completely by solid-state NMR data, and the structure is shown here. It has a backbone RMSD of 0.9 angstrom, so it is quite well defined, of course, excluding the loop, for which we have absolutely no structural data, because we don't even see the resonances. And of course, we used also some angular restraints derived by chemical shift, kind of chemical shift index for the RNA, and some mild restraints on the backbone torsion angle for the regions that we know are in a stem, are part of a stem. So this structure is also quite close to the structure of other RNAs of this class that are bound to proteins and that have been solved by X-ray crystallography, so not specifically this RNA. As I said, this complex does not crystallize, but similar RNAs. And what you can compare is, for example, the kink angle between this stem and this stem. And this is in a range that is the same or very similar to what has been found in other crystal structures of this of RNAs of this class. So we were quite happy with it, and we decided to go to the next step, and namely to the measuring RNA-protein interactions by solid-state NMR. And here we started very with in baby steps, so to say. So we first developed a phosphorus 15N Tidal experiment that could give us the correlation between the backbone 15N of the protein and the phosphorus of the RNA. And in this complex, there is a phosphorus that basically penetrates a cavity of the protein. And here you see, and this is the phosphorus of the U20, and here you see all the Tidal correlation of this phosphorus with different nitrogens of the protein. Together with Ben Reif, we also developed another experiment that is based on acquiring at 50 kilohertz spinning rates, so on a 1.3 millimeter rotor, a 15N proton correlation of the protein in the presence of either protonated RNA or deuterated RNA. In the presence of the protonated RNA, you of course lose some of the signal due to the HH dipolar couplings, while in the presence of the 2H RNA, you have more intense signals, and this difference in intensity is of course dependent on the distance between the RNA and the protein. So by quantitatively analyze the spectra, and you not only can get an idea of where the RNA is binding on the protein, kind of chemical shift perturbation, equivalent in solution state NMR, but you can also extract some useful distances between any proton of the RNA and these amide groups of the protein. And this is what, as I said, we did in collaboration with Ben Reif in an early paper. More recently, we have tried to basically go a little further and measure many distances between the protein and the RNA. And we decided to do so by measuring paramagnetic relaxation enhancements. And here I would like to tell you a little bit more about this. What we did is we acquired the spectra of the protein in isolation and in the presence of the RNA, and we quantified a series of chemical shift perturbations. These chemical shift perturbations are depicted here, and you see in green the amino acids that are solvent exposed, and in brown the amino acids that are not solvent exposed but that are exhibiting chemical shift perturbation. So you can say that the RNA is, you can confidently say that the RNA is binding to this surface. Once that we have identified the surface of the protein that binds the RNA, we engineer positions where we insert a cysteine mutation to couple this position with a paramagnetic tag. And we do it, of course, as one usually does in solution NMR spectroscopy, one by one. Then we generate different samples with the paramagnetic, with the paramagnetic tags in the different position, and we measure a carbon-carbon correlation of the RNA in the presence of the free electron. So we coupled it normally with a natroxide type tag, and after reduction of the tag to the diamagnetic state. And we obtain, of course, difference in intensity between the peaks measured in the paramagnetic state and the peaks measured in the diamagnetic state, and we interpret this difference in intensity in terms of distances between the paramagnetic tag and the corresponding position of the RNA. Now, of course, in this case, and I will not, let's say too much about that because of the time constraint. In this case, we cannot analyze this difference in intensity as accurately as we do it in solution state NMR, or as it was published before by Chris Jaron for T1 measurement. And the reason for that is because of the because we are not able to measure really nice R2 or R1 raw decays in this case because of the short, let's say, lifetime of the carbon of the RNA and the low concentration of the low signal to noise. So not being able to measure a real R1 raw in the para and in the dia condition, what we did is to let's say derive an empirical correlation between the intensity of these peaks and the distances from the paramagnetic tag, and this is explained in this paper. So we used both these distance-derived restraints and the chemical shifts in HADOC, and we obtained the structure of the RNA-protein complex, which is shown here in blue, and is very, very similar to a structure of a complex of this family. As I said, this is not the same complex, it's just a complex of this family, solved by X-ray crystallography, which is shown here in gold. So we were quite satisfied with that, and we concluded that with our paramagnetic relaxation enhancement method, one can solve protein RNA structures by solid-state NMR, and this is again the first protein RNA structure that was solved by solid-state NMR. I mean, now one could ask, why don't you just measure, let's say, distances between the protein and the RNA in more classical ways? Why do you have to do this with paramagnetic relaxation enhancement methods? The reason is because this surface is usually not very, I mean, the two molecules are actually not so close, especially in terms of heteronuclei. And all the carbon-carbon or carbon-nitrogen transfer in at the surface, they actually don't work, or they deliver a very, very little signal. One could do that by using DMP, of course, but we do not have the possibility of doing DMP. We were looking into that, but then we never went on with this. So if we want to measure the distances here, we really need to look at hydrogen atoms. And because of this, and also to get rid of the need of making different RNA samples to assign, so with selective labeling to assign such a small RNA, we decided to look into proton acquisition. And here I show you an HSQC of the, so an HSQC-like experiment of the ribose region of the RNA at 20 kilohertz, 40 kilohertz, 60, and 109. And you see beautifully how the fast rotation let's say, gives rise to interpretable line width for the protons. And here I plot the coherence lifetime of the proton at different MIS frequencies. And as you see, we reach coherence lifetimes of about 4 milliseconds for the protons in position H1 prime of the sugar, or the protons in the base, while the other protons of the sugar, which have a lot of proton-proton coupling, they have coherence lifetimes of only a little less than 2 milliseconds. Of course, if you compare this coherence lifetime with this line width, you still see that there is still a good portion of non-homogeneous broadening in this line width, and this is probably intrinsic to all to the RNA per se, because, as I said, RNA molecules are usually much more flexible than proteins, so this RNA RNA may still be present in different conformations. So here it's a zoom of the proton-carbon correlation in the base region. You can recognize and assign really all peaks of this RNA similarly as you would do for a solution state NMR spectrum. And now let's see how we assign this RNA and which kind of experiments we have developed to assign the RNA. So for assigning the ribose and the base the spin system, so the carbon of the ribose and the base spin system, and in particular for connecting the ribose with the base, we use HCN ribose and HCN base kind of experiment, similarly to what I've shown you for the non-proton detected version. Here what I show you in red are the peaks from 2D planes of a 3D experiment at the frequency indicated here, overlapped on the HSQC spectrum. And as you see, we can see many of the peaks of the RNA. We can actually see almost all of the peaks of the RNA, and we can make connections between the base and the ribose through that. And what I should also say is that the additional intensity of the proton detection is also allows us to run a three-dimensional spectrum. So for the spectra that I've shown you for the heteronuclear detection were mostly two-dimensional spectra. We were able to run some three-dimensional spectra, but we could not go lower than an acquisition time of several days, while here we obtain those spectra in a little less than 1 day, and we have the resolution of the 3 dimensions. To assign the spin system in the sugar, so the carbon and proton spin system in the sugar, we use a normal HCCH TOXI kind of experiment, which is the same that you would use in the solution NMR. And by combining these two experiments, you can obtain a complete assignment of the ribose of the RNA and a connection to this nitrogen and to the carbon of the bases. Now, one of the main problems in spectroscopy of RNA, in NMR spectroscopy of RNA, is to get actually the assignments of all the nuclei in the base. And this is very difficult in solution state NMR because many of the couplings are actually quite small, and so that it's quite difficult to go from what you would usually have assigned, which is the C8H8, all the way through the bases. But let's say the fun part in an RNA actually happens here on the surface. So it is quite necessary to connect what you have assigned here, which is close to the backbone of the RNA, to this face here of the base, or this face here of this base, or this here of this base, which is then the one which connects the two strands of the RNA in the helices. And for this, we also have used, of course, in solid state NMR, you can use dipolar couplings, so you are not limited to scalar couplings. So assigning carbons of the bases is much easier. And here you see an HCCH kind of experiments where you see a complete correlation from the H8 or H6 of different nucleotides to all the carbons of the spin system. And similarly for an HCNH kind of experiment, you also see the correlation from this HC to the nitrogen and to the protonated nitrogens here. So basically N1H1 or N3H3 or N6H6 of the adenosine. There are, of course, some systems, so some spin systems where you cannot get the complete assignment with this kind of experiments. And for those, we have designed other experiments which are also contained in the paper that we just published. But again, for time reasons, I will not go into all these experiments, but I would just show you how it is possible to obtain base pairs very easily. So here in this RNA, we have 4 kinds of base pairs: normal Watson-Crick base pairs, so HU base pairs and GC base pairs, but also non-canonical base pairs, AG and UU. And in order to obtain the Watson-Crick base pairs, we developed experiments which are called HNHHCH, where basically we start from a protonated nitrogen. We go through the proton-proton RFDR over these distances, for example, or in this case here, to the other nucleotide, and then we read the magnetization on the CH. And here, for example, you get the correlation between the N3 and the C2H2 of the A's, and in the GC base pairs, you get the correlation between the C's N4 or H41 and H42, and the iminos of the G's. And here again, you see in red all the planes from a 3D, the peaks from the planes of a 3D experiment on the top of the 2D HSQC. And with similar experiments, you can also get the non-canonical base pairs, like UU base pairs, through the correlation of these 2 groups here, also transferred through an RFDR-HH, and these other non-canonical base pairs through an HH RFDR, for example here, but also through the contacts between this H6 and the H1 prime, read in this other kind of experiment. So by doing this, we are able to assign all the base pairs and all the protons of this RNA. And here now, I would like to conclude, because I already spoke too much. We think that solid-state NMR study of RNA of moderate length is possible with a quality that is similar to a solution-state NMR. And we now are going to develop 1H detective experiment to obtain structural restraints. But how do we really bring this to then big complexes and big RNA protein complexes? We think that this will be possible if we label the RNA piece by piece. So we don't think that ever with spectroscopy, with any kind of NMR, no matter if in solution or in solid state, you will be able to look at RNAs of 200 nucleotides at atomic resolution, because there is just too much overlap. But if you're able to segmentally label RNAs or pieces of RNAs, and for sure we are able to do that, so there are the technologies to do that, one with solid-state NMR would now be able to study at atomic resolution these pieces of RNAs in the context of very large complexes. And to conclude, I would like to thank the people who did the work. This was the work of, the 1H detected experiments that I showed you last. This was the work of Philippe Aguillon. The protein RNA complex with the PREs was done by Mamdouh Ahmed. But really this solid-state RNA work is a long-lasting collaboration with Alexander Marchanka, who was first postdoc in my group at the MBL, and now he's an independent group leader who really pushed this project to the state where it is now. And I would like to thank you for your attention and leave you with a beautiful view of the new, well, not new, but for me new, Birmingham NMR Center with this brand new 1 gigahertz spectrometer we just came to field 10 days ago. And I thank you for your attention, and I'm happy to take questions.
Okay, a very nice talk, Teresa. Lots of new results, all right? At least I think they're new. Maybe I haven't seen them before, maybe a few weeks ago, but anyway, beautiful, beautiful work. So one of the questions I had, and I'm not sure, maybe you answered it, but maybe I missed it. So you should be able to see T-DORs. If you had at least the right specifically labeled RNA, you should get T-DOR contacts between 2 base pairs, a whole bunch of carbon-nitrogen contacts. Mm-hmm. Have you ever, did you try that experiment? Or I mean, you've done things very similar to this, but I mean, if you go back to your slides where you were talking about the T-DOR, the 3D, well, were those?
They are not so close, carbon and nitrogen.
They're not so close.
So the carbon and nitrogen, so the closest that they are is about 3.5 angstrom. So yes, you do see some, but it's better to go with nitrogen, and for sure better to go through the protons that are in between.
Oh, with the protons there, that's another parameter that I had another approach. But I mean, the problem with solution NMRs, you've really got 1 proton or so on each of the bases, times 2. So there are not a lot of constraints in the proton.
Yes.
In the node spectrum, and that was always an issue. But is this your? Yeah. So anyway, I mean, 3 angstroms, you should be able to see the carbon nitrogen.
Yes, 3 angstrom we see, but I mean, 3 angstrom is let's say I mean, they are more like 3.5 or further, the carbon and the nitrogen, and there we have difficulties to see them. I mean, we see some, but not all of them. And for sure, we had much more luck in having the nitrogen RFDR for the one where both the donor and the acceptor are nitrogen, of the protons are nitrogen. So for those base pairs, which let me just get the base pairs again here. Yeah, exactly. So here, for example, when we were doing the heteronuclear acquisition, we just did nitrogen RFDR, and these are, let's say, quite close. I mean, as you see here, this carbon and this nitrogen are actually far away. This carbon and this nitrogen are actually far away. This one and this one are also far away because they're not completely one. So it's not so. They are quite far. It's not so easy to have a T-DOR that tells you all of them.
That's across a base pair. I was thinking about the stacking, the vertical stack.
Oh, they are even more. They are 4 point something. This we tried. Quite intensively, and actually we also tried with selectively labeled nucleotides. So with RNA that are selectively labeled at individual positions in order to, let's say, eliminate all possible dipolar truncation and whatever. With Tidal, we were never able to see anything. I think we were able to see something through to a proton-driven spin diffusion experiment. Let me recall that. I mean, we even never published it because of all the stacking. We saw maybe 1 or 2 of the positions we tried, but they are far. I mean, they are 4.2, 4.5 angstrom.
Yeah, well, those still should be within shooting distance, I think. Yeah, I mean, at least they are in cases where I mean, you could try one of Chris's you're running XFS redoors too on that.
Okay.
Anyway, okay, so there are a couple of questions here from Sahil. You have used H-bond information for calculating structure of RNA by solid state NMR. How did you identify H-bonds in RNA?
So, I mean, this is a typical, it is typical in RNA structure, RNA structures that you just, for example, see this imminous proton here. And if you see this imminous proton, you say it is involved in an A bond, in an H bond. Because if it is not involved in an H bond, then you wouldn't see it. And then basically, if it is involved in an H bond with a C, then you just give also these other things, even if you don't see them. So this is what is typically done in solution state NMR. So it's a very, let's say, rough way. What you can also do in solution state, the reason why I'm saying that is it will be clear in a second. What you can also do in solution state NMR is, for example, to measure this nitrogen-nitrogen coupling that is hydrogen bond mediated. But that's about it. So there is not very much else that you can do. And here in solid state NMR, of course, we do not measure hydrogen bond mediated nitrogen-nitrogen couplings, but I mean, for a large RNA, you would not do those also in solution NMR. So what we do is we just rely on distances. And so we fix basically the distances because we know that we have a short distance, for example, between this N1 and then N3, because we have seen this this contact here, or that we have a short distance between this H3 and the H2, because we have seen it in this experiment here. So basically, we have seen this transfer here. And we rely on distances to identify the base pairs, and then we impose the hydrogen bond. So we do not directly measure the hydrogen bond in terms of also like doing exchange experiments or measure J couplings as in solution state NMR, but we just have distances, and then that define the geometry of the two bases, and then we impose the hydrogen bonds.
Okay. And Eric, Johan has a question. Do you expect pre-PRE quantification better if higher mass or field is applied? And you mentioned the lifetime issue. Is that correct? Is that right?
Yeah. So basically, so what Chris did is, of course, to measure the T1 times, and to use metals, paramagnetic metals, to elicit an effect on the T1 times. So for RNA, we could not use, or we chose not to use metals because these also bind to the RNA. Okay, one would have had an EDTA tag that captures most of the metal, but you are never sure that then they would not bind to the RNA. So we decided not to use divalent cations in doing this. So like manganese or so in doing our for doing our PRE measurements. So we had the nitroxide tag. Now, if you have the nitroxide tags, you barely have an effect on T1. You only have an effect on T2. So in order to quantify them precisely, you would have to measure really T2 in the presence of the radical and in the absence of the radical. And this, with the signal to noise that we had, would have taken months. And we decided not to do that. So unless you can do that with the nitroxide, then you cannot measure basically PREs in an accurate way. And I mean, you can also, let's say, estimate it as in in the solution state way by estimating the intensities of the peaks, but then you still need to know the gamma 2 of the nuclei that are involved. And this again needs a lot of time and attention to measure. The other thing is that you are never sure that you really only have a direct carbon-carbon transfer. So it is also possible that you have leakage to other carbons. So this is also something that you need to consider, and that somehow your quantification is that makes your quantification not completely correct. So because of all these reasons, we decided just not to do a correct quantification, but use an empirical correlations. And what we did is we basically measured the intramolecular PREs between these tags and the protein itself. And then we defined the linear correlations between the difference in intensity and the distances. And then we said, okay, this linear correlation should be applicable also to protein RNA distances, not only to protein-protein distances. This is, of course, also, again, an approximation, which may not be true, but we used it, and it worked. So, of course, there is much more to do and to make better. We are happy if also somebody else starts working on solid state NMR of RNA and optimizes these experiments as well. So there is only so much that we can do, so to say.
Yeah. Okay, all right. So I think we should probably move on to the second speaker, who is Daniel.
Okay, I stop sharing. Okay,
if you could stop sharing, yes, okay. So Daniel Jardon-Alvarez, he started out at Ludwig Maximilian University, I think in Munich. He got his PhD at the University of Sao Paulo, and then was a postdoc for a while at Ohio State with Phil Grandinetti. And more recently, he's moved to a second postdoc with Mikhail Leskis at the Weizmann Institute. And today he's going to tell us about, he's going to give a presentation entitled From Pre to DNP. Okay, so Daniel.
Okay, so thank you very much for the introduction and for the opportunity to show some of our work here. Okay, so what I want to talk today about is what we can learn about DNP if we understand the paramagnetic relaxation enhancement from the polarizing agent that we introduce into the sample. And in our group, we are mostly interested in inorganic materials. And inorganic materials often have a nucleus that would be relevant to study and which have very low sensitivity. And it would be good to increase the sensitivity by doing DNP for this type of nucleus. So in the context of magic angle spinning NMR, what many groups have been doing is to dissolve the sample of interest in this so-called DNP juice, which contains some organic radicals. And then upon microwave irradiation, you can transfer the polarization from these unpaired electrons to the nearby proton nuclei. And then through proton spin diffusion, you're able to transfer the hyperpolarization to the surface of the sample. In this way, it is possible to obtain very large enhancement, but they are limited to this, or mostly specific to the surface. And you won't get that much enhancement for the bulk nuclei. So in our group, we are doing a fundamentally different approach, which consists in introducing the source of polarization, the polarizing agents, directly into the bulk of the samples. And we do this by doping our samples, which are normally inorganic oxides, with paramagnetic metal ions. And this way, when we then irradiate the samples with microwave, we are able to get polarization enhancement of nuclei that are in the bulk of the sample. And we have shown that this approach gives us good results in a series of different systems. So we were able to get really nice enhancement of low sensitivity nuclei in the bulk of inorganic materials. And here I'm showing you a few examples from our group. So we use as polarizing agent some variable metal ions, so for instance, manganese 2, iron 3, or gadolinium 3, and we were able to get a great enhancement for these low sensitivity nuclei, yttrium-89 or oxygen-17. And we also worked a lot with lithium-6. But today, I don't really want to focus on applications. Instead, I want to try to answer some more fundamental questions, which are, first of all, how is it even possible that we are able to obtain this large enhancement when spin diffusion will not play a role at all in transferring the polarization from the unpaired electrons throughout the sample? And then the second question that I would like to address is if we are able to get some answer on what would be an optimum doping concentration for these type of experiments. And in order to answer both of these questions, what we have to do is to understand what happens in terms of the magnetic resonance property in our samples if we introduce paramagnetic ions into it. So the first thing, these inorganic solids are very rigid normally, and therefore they have very, very long relaxation times. And as soon as we start introducing paramagnetic species, then the relaxation times are going to drop in an effect that is known as paramagnetic relaxation enhancement. And then if we keep increasing the concentration of paramagnetic species, at some point we're also going to shape the appearance of the NMR spectrum completely due to the importance of new interactions such as dipole coupling and Fermi contact shifts between the new introduced electrons and the nuclei. And these two effects can ultimately also lead to an effect that is known as signal quenching, which means that there will be some nuclei that we won't be able to observe with NMR because they're just too close to the paramagnetic center. Now, in terms of the EPR properties of the unpaired electrons, at the very low concentrations, the EPR properties of these metal ions will be governed by the interactions of the metal ions with the lattice itself. But as we start increasing the concentration through space and exchange interactions between the electron spin start becoming more and more important, and they start dominating also the EPR line shape. And finally, in terms of DMP, one could imagine that there should be an optimum concentration for the different DMP mechanisms. And this is something that we would like to learn more about. So, but today I hope I will be able to convince you that if we are able to understand and measure the paramagnetic relaxation enhancement effect, we will be able to answer and to understand many of the other properties that I'm showing here. So let me start by giving a quick reminder of NMR relaxation in general. So NMR relaxation is mediated by a random fluctuation of local magnetic fields, and specifically longitudinal relaxation is mediated by fluctuations at the Larmor frequency of the nucleus. So in order to quantify how much for given frequencies present in a random fluctuation, we looked at the so-called spectral density function, which is shown here and looks like and is a Lorentzian. And this tau c is the correlation time of this random fluctuation. And transverse relaxation is in addition also caused by slow fluctuations of fields that are actually parallel to the external field, and this way they will cause some dephasing of the magnetization in the transverse plane. So we write the spectral density at 0 frequency with it, which is just the correlation time of the fluctuation. So with these two equations, we can draw the famous figure of relaxation where here it's plotted the relaxation time versus the correlation time that causes the relaxation. And we see that T1 passes through a minimum whenever the correlation time is equal to the inverse of the Larmor frequency, while T2, on the other hand, just becomes shorter and shorter as we increase the correlation time or slow down the motion. And so the next question is, why does introducing paramagnetic metal ions cause relaxation, increases the relaxation in solids? And so first of all, you need to know that in this rigid solid, the motion are very, very scarce, and therefore relaxation times can be very, very long. And as soon as we start introducing paramagnetic metal ions, we are not introducing, at least not significantly, any new type of motions. But what actually causes the relaxation is the relaxation of the the relaxation of the electron spin itself. So as this magnetic moment of the electron spin starts fluctuating due to its own relaxation. So I should say that electron spin relaxations are much more efficient than nuclear relaxation. So this will be orders of magnitude faster. as this starts oscillating, nearby nuclei are going to feel these changes in the position of the magnetic moment of the electron as a fluctuation of their own local fields. So this will cause relaxation. And this way we can write the equation for relaxation in complete analogy to what I showed before, where here the prefactor is just the strength of the interaction squared. So in this case, it's the through-space dipole coupling, which is going to be the relevant interaction in most of our samples, times the spectral density at the nuclear alarm frequency. And now the interesting part to note here is that the correlation time of this motion is just the electron relaxation time, so T1e. So I'm not going to write T1e here. Instead, I'm using tau1e in order to allow for the possibility to also coherent effects be a source of relaxation, although they are not strictly speaking electron relaxation. And we can write the exact same, the analogous expression for T2 as well, where we have here now the spectral density at 0 frequency. And with these two equations, we can again draw the figure of relaxation versus correlation time, where now the correlation time is the electron relaxation. And this equation is based on a given distance between the electron and the nucleus, which is going to determine the strength of the dipole interaction. Now we can imagine what would happen if we put the two spins closer together. We're just going to have a stronger interaction, and therefore the relaxation time is going to be shorter. And now if we look at this curve more carefully, we see actually that the shape of the curve has not changed. So note that this is a log-log plot. And even more, we see that the ratio of T1 over T2 stays actually constant, independent of the distance between the electron and the nucleus. It just depends on the value of the correlation time or the electron spin relaxation. We can do this, show this also mathematically, just by dividing the longitudinal relaxation over the transverse relaxation times, the T1 over T2. And we see that this expression only depends on the electron relaxation time and the nuclear alarm frequency. But this way we have a nice tool to compute, to measure the electron spin relaxation just by measuring T1 and T2. And this is going to be the tool that I will be using in the rest of the talk. And I should mention that this relation has already been noticed before. So this was, for example, showed up in a paper by the group of Jaron. So the next thing that we now want to do is prepare some samples. And we did a full series of samples based on the structural lithium magnesium phosphate. And we replaced magnesium, which is diamagnetic, by manganese 2, which is paramagnetic in nature. And the nice thing about the specific structure is that we are able to substitute it from 0% all the way to 100% without changing the crystal structure at all. However, there will be some small changes in the unit cell parameters due to the difference in ionic radii. And we can actually follow them from the X-ray data. And we see that, for example, the unit cell volume is growing linearly with increasing manganese concentration. And this linear relation is actually a nice indication that this doping or this exchange of magnesium and manganese happens in a homogeneous way throughout the entire structure. Then the first thing that we characterized was the electron spin properties of these samples. So we looked at EPR spectra of manganese 2, which is spin 5 half, and we measured at different frequencies. So here are the results for X, Q, and J band. And what we for a very low concentration of manganese first. And what you see is that at these low fields, we get a really complicated line shape where it's even difficult to distinguish between what is noise and what is the actual signal. But as we go to higher fields, we get narrower or more better resolved lines. And the reason for this is just that the central transition of the EPR line scales inversely proportional with the magnetic fields. But higher fields, we get nicer spectrum. And then we also see the characteristic sextet of manganese EPR, which comes to the hyperfine interaction between the manganese electron spin with its own nucleus, the manganese 55 nucleus, which is also 5 half. And next we measured EPR for all the different concentrations. So here are a few spectra. And what we saw is two different effects that happens when we increase the concentration of paramagnetic center. First, at this low to intermediate concentration regime, the individual features of the spectrum start becoming broader and broader. And we can attribute this to through-space dipole interaction between the electrons. So as we increase the concentration, the mean distance between just becomes smaller. And then at some point we reach a higher concentration, where the exchange interaction between the electrons starts becoming not the dominant interaction. So the exchange interaction is kind of like the EPR equivalent of J couplings. And at that point, the line shape becomes narrow. And this is a well-known effect, and it's called exchange narrowing. And finally, what we wanted to do is also measure electron relaxation time of these samples. However, this turned out to be really challenging because the electron relaxation times are very short. And this way, if they become too short, we are not longer able to even detect an echo to be able to map the relaxation times. So, however, we were able to measure it for these lowest concentrations, which has the longest relaxation times, to a temperature of about 100 Kelvin, which is the first temperature which starts being of interest for us if we want to do DMP at this temperature. And that's what I want to say here is for this lowest concentration, we get a T1E, which is around a few microseconds. And for T2E, we observed that over the entire temperature range, T2E is more or less 1 order of magnitude shorter than T1E. So with this, now we turn our attention to the NMR. And this sample is nice because it has many nice NMR active nuclei, like phosphorus 31, lithium 7, and lithium 6. And here I'm showing you the spectra for that, some of the spectra for different concentrations of these 3 nuclei. And more or less, we observe exactly the same trends for all nuclei. So at very low concentrations, we start to see a significant broadening, which is homogeneous in nature of the NMR line, until we reach a certain point where the NMR line becomes narrower again. And at this point, we also start seeing the appearance of spinning sidebands. You can see it nicely here for the lithium 7, and we also see some significant shifts of the main peak. And the reason for this is that for the spinning sidebands is the through-space dipole couplings between electron and nuclei. And the reason for the shift is that the Fermi contact interaction starts becoming important at these high concentrations. Now, the effects are also the same in phosphorus 31, but here the bonds are much more covalent, and therefore the Fermi contact interaction will be much stronger. And we can see that the shifts are significantly more important. So here we obtain a shift of about 8,000 ppm, while here the shifts are something like 70 ppm. And so the next thing that we did was to quantify the signal intensity in these measurements. And we did it for lithium 6 because lithium 6 is kind of the cleanest nucleus among these, because we're able to excite the entire NMR spectrum with a single carrier frequency, while especially for phosphorus, we needed many carrier frequency to map the entire spectrum. So, and here's the results that we obtained. So the lithium 6 intensity starts dropping when we increase the concentration of manganese ion. So this is known as quenching. And at some point it starts dropping significantly, but then suddenly this trend changes and we start being able to observe more and more lithium 6 nuclei again, until we reach this high concentration regime where we are virtually able to measure all the nuclei in the samples. And this figure is kind of nicely closes the gap of what was shown in the literature. So here are some results of this low concentration regime of paramagnetic centers. So here from our group, and also in a more systematically way, it was done by the group of Jan Schmidt after Gunne, where it was shown that with increasing concentration, the signal decays. However, if you would extrapolate these curves, you would expect that at very high concentration, you should not see any signal. But we know that analogous samples where the paramagnetic center now is a major constituent of the composition, we are actually able to observe the NMR signal. So it means that we are able to observe even the nearest neighbors in the first coordination sphere of the paramagnetic center. So what is going on here? So and the only possible explanation for the sudden change here is that the properties of the electron spin themselves is changing. And what is actually changing is the electron spin relaxation time. So in order to map these changes, we're going to look again at the nuclear relaxation behavior. So here I'm showing you the T1 and T2 relaxation times of lithium 6 for the varying concentration of manganese in this sample. And you can see that at this low concentration regime, T1 and T2 decrease rapidly. Note that I'm showing here a logarithmic scale. And they follow the trend that we would expect, shown here as dashed line, which is that T1 and T2 decrease are proportional to the inverse squared of the concentration of paramagnetic center. So this is well known that to be the effect when spin diffusion does not play a role in relaxation. And then we reach a point where actually T1 and T2, they start bending, and at some point they change their trend. And even though we're still increasing paramagnetic concentration of paramagnetic center, we're actually increasing the relaxation times. So now to study this a little bit more in depth, we're gonna take the T1 over T2 ratio that I introduced in the beginning. So what we see here is just dividing T1 over T2. And what we see here is that at this low concentration regime where they follow the dashed line, and there is basically no change in this ratio until we get to this point where the T1 over T2 ratio starts dropping dramatically. And as I said before, we can obtain the electron relaxation time out of this T1 over T2 ratio. So this is what we did just with this simple equation. And we see that for this very low concentration, we get a T1e of approximately 0.8 microseconds, which is kind of in the right order of magnitude if we compare it to the relaxation times that we measured at 100 Kelvin, but with pulse EPR. And then this T1e starts dropping quickly as we keep increasing the concentration. And actually we can take until it reaches to 1, which is the limit of what we can observe, right? Because T2 is not going to become longer than T1. And we can take this a step further and actually try to model this decay. And we observe that this follows nicely a trend where T1e is proportional to the distance between the mean distance between the manganese-manganese electron or the manganese electrons. So the mean distance between two manganese to the power of 6. And this type of relation is what we would expect if this decay of T1e is driven through dipolar interactions, through space dipolar interaction between the electron spins. So meaning that the values of tau1e here are actually good values of T1e, so the electron relaxation. So trying to summarize what I've talked about until now, showing here the relaxation data again and the quenching behavior, and now we're going to compare this with the graph, the BPP model, right? So at the very low concentrations, we have a very long correlation time. So we must be somewhere here in this figure, where T2 is very short and T1 is relatively long. So in this type of scenario, because T2 is strongly affected by the paramagnetic center, there will be a lot of nuclei that we are not able to detect. These are the quenched nuclei. So we can imagine that from every paramagnetic center, we will have a large quenching sphere. Now, as we start increasing the concentration, we will get more and more of this paramagnetic center, and we start seeing a decrease of the signal intensity until we reach a point where the manganese ions become so close together that the T1e of them starts dropping. But at this point, we start moving from the right to the left in this figure. And as we do so, we start reducing the quenching radius of T2. So there is now a competing effect between decreasing radius of each paramagnetic center and increasing total number of paramagnetic center. And this is what's happening here. So we move from this decreasing of the signal intensity to a sudden change and back to increasing this. And at some point, the quenching radius becomes so small that we are able to detect even the nearest neighbors of this paramagnetic center, and what we observe over here. Okay, so at the beginning, I said I wanted to talk also about DMP. So we know, and I will talk about it in more detail in a second, that DMP, for good DMP enhancement, we need long electron relaxation times. So if we try to do some DMP on one of these samples, we would choose a sample where we have low concentration, because here the electron relaxation times are longest. And I'm showing you here the field sweep profile that we measured for this particular concentration. And we get a moderate but nice enhancement of about factor 11. Now, if we try to measure the DMP enhancement at different concentrations, we see a dramatic drop in the enhancement, so from 11 to 3, and then we have no enhancement at all, because T1e just becomes so short. So is there a way that we can try to be a little bit more quantitative of how the DMP enhancement depends on T1e? And in order to answer that, we have to look at the theory of the DMP mechanism involved here. So the relevant DMP mechanisms for all our samples is the solid effect. And we can understand the solid effect by looking at the energy level diagrams of one electron coupled to one nucleus, shown here. And the idea of the DMP solid effect is to irradiate in one of these formally forbidden, either double quantum or zero quantum transition, and this way create a hyperpolarization on the nuclear transition. And in fact, we can quantify the degree of hyperpolarization of the nuclear transition just if we know the degree of saturation of this transition that we are irradiating on. So this is shown here. So we need to quantify the saturation efficiency, and then we can know the enhancement, the DMP enhancement. And we know how to calculate saturation efficiency just by following the Bloch equation of saturation. So this is shown in this equation here, where the population difference between the two energy levels that are being irradiated is equal to the difference at the equilibrium divided by 1 plus the nutation frequency squared. But note that now the nutation frequency is actually the effective nutation, which is scaled by the dipolar coupling strength over the Larmor frequency, and then times the transverse relaxation time times the longitudinal relaxation time. And here we have to take into account all possible relaxation pathways that are trying to counteract our efforts to saturate this transition. And then we were looking at this equation for a while, and then we realized that actually if the nuclear relaxation time is governed by the paramagnetic relaxation enhancement due to the polarizing agent itself, then this whole expression here becomes independent of the strength of the dipolar coupling. So we can cross out the strength of the dipolar coupling of this equation. But this means that the DMP enhancement is actually independent of the dipolar coupling strength. And this is going to be valid as long as the nuclear relaxation time is governed by the paramagnetic relaxation enhancement from this electron. And this result has huge impact for us because it ultimately means that the enhancement is also independent of the distance between the polarizing agent and the nucleus of interest. And this is actually the reason why we are able to get this large enhancement in our samples just by doping it with small amount of paramagnetic center, because the signal is just independent of the enhancement is independent of the distance. So we can get actually homogeneous enhancement throughout the entire bulk of the samples. And here are some numerical simulations to prove this point, where we see on the y-axis the polarization, the DMP enhancement as a function of the distance. And you can see that it doesn't change at all with increasing distance. However, it has a strong dependence on the electron relaxation time. So as the electron relaxation times become shorter and shorter, it becomes more difficult to saturate the transitions, the transitions that we are irradiating with microwaves. And then we also have some experimental evidence to underline our point. And this is that we observed that so for this, we looked at a different sample now. So we doped this lithium titanium oxide with iron 3. Iron 3 is also paramagnetic in nature. And we saw that over a large range of concentration, the enhancement was not changing. So over an order of magnitude of different concentration of iron, we will always get the same signal enhancement. And the reason for that is again, just that as we increase the concentration, we're just reducing the mean distance, but this does not change the signal enhancement. It just reduces the build-up times. However, there is a limit to this. And there is a limit on both sides. So at very low concentration, at some point, the intrinsic relaxation of the nuclear that is independent of the paramagnetic center starts becoming important. And at this point, those very remote nuclei are not longer being enhanced by the same factor, and the enhancement should drop. And also at the high concentration regime, at some point, the through-space dipolar coupling between the electrons becomes so relevant that the electron relaxation time starts to drop, as we saw before. And then also the DMP enhancement that I showed you here is going to be less. So, and then the final step that we wanted to do is actually trying to be even more quantitative. Can we directly correlate the electron relaxation time to the DMP enhancement? And for that, we looked at one specific sample. So this one over here. So this lithium titanium oxide doped with a mole fraction of 0.01 in iron 3. And we mapped the DMP enhancement as a function of the temperature. And this is shown here. So here you see the enhancement. And it decreases as we increase the temperature. We went from 100 Kelvin to 300 Kelvin. And at the same time, for all these measurements, we were also measuring T1 and T2 of the nuclei. And here I'm showing you the ratio of T1 over T2. So now if we take this ratio and recalculate the electron or T1e or tau 1e from this, we can plot the DMP enhancement versus the T1e. And what we observed was actually a linear trend over the entire temperature that we measured. And so the final question is, can we also understand this effect from our theoretical expression? So here I'm showing you again the saturation efficiency, now distilled down to the relevant parameters. And you can see that if T1 and T2 are changing together, which we would expect, and we saw in the EPR measurements, then one would expect a quadratic dependence of the enhancement and T1e. And this is shown here in the figure as this dotted line. However, we have to be aware that there is actually a theoretical limit to the DMP enhancement. And this theoretical limit is going to bend the curve. And we can actually see that around the saddle point of this bending, the enhancement is actually following a linear trend with the T1e over a very large range of enhancements. And actually, we can see that the enhancement is linear in the electron relaxation time regime that we determine for our sample, if we assume that T2e is about 1 order of magnitude shorter than T1e. And this is again in good agreement with what we saw in EPR on the similar sample. So to summarize this, if you have a polarizing agent and you want to predict if it could be a good DMP polarizing agent, a simple test you can do is just measure T1 and T2, determine if these are dominated by paramagnetic relaxation enhancement, and then if this is the case, you just take the ratio and look what type of T1e you get, and if you expect to get any saturation with the T1e that you measure. And with this, I would like to conclude. So I hope I was able to show today that the DMP enhancement can be independent of the distance between the polarizing agent and the nucleus of being polarized, as long as the paramagnetic relaxation enhancement is the main source of relaxation. And secondly, I showed that it's really relevant to map the paramagnetic relaxation enhancement properties of the samples, and that we can understand a lot of things if just by looking at the ratio of T1 over T2 in terms of DNP enhancement, but also in terms of NMR line shapes and quenching behaviors. And finally, some advertisement if you are interested in this type of studies. We recently published a chapter in a book about the DMP and inorganic solids using paramagnetic metal ion dopants as the source of polarization. And here we talk a little bit about some theoretical concepts that some of them I presented today, but we also give some practical considerations and tips to implement this type of DMP in your own lab. So you might want to have a look at this. And with this, I would like to conclude by thanking, first of all, and most importantly, my PI, Michal Eskes, but also all my colleagues from the group, and Tahel, who made most of the samples that I showed today, Hans van Tol, who did all the EPR measurements at J-band, so at high field. And I also would like to thank my former group and my former PI, Philip Grandinetti, for many discussions on paramagnetic relaxation enhancement, which turned out to be really useful in this project. And of course, thank to all of you for listening.
Okay, thank you very much, Daniel, for really some really nice insights into inorganic solids. Kong, do you want to start off the questions?
Oh yeah, sure. Yeah, I'm just curious. So I think in one of your field profiles you have the enhancement factor of 11, 3, or 1. But I'm just curious. Can you tell us a little bit more about the DMP build up time for these experiments?
Yeah, I mean in all these experiments, basically the DMP build up time is about T1. So T build up is more or less the same as T1. And the reason for this is just that T1 is the limiting factor in the enhancement over here. So we are not reaching the theoretical limit that would put us faster. So yeah, so
I mean like the T1 DMP.
Yeah, T build up and T1 they go hand in hand. So we observe.
Yes, like can you give me a physical number?
Physical. I mean,
Yeah.
it depends on the concentration. So
Yes, exactly. So
yeah.
can you give me some numbers?
Yeah, I mean, I can look at the figure here again. So
Yeah. The
so
next one,
here we were at the lowest
550.
concentrations. We were for lithium-6, like hundreds of seconds, and I mean we go like up to tens of seconds, I would say. And if we go further down with T1, then T1e starts becoming also short. Like the concentration then becomes too long. So somewhere between tens of seconds to hundreds of seconds as T1. Yeah.
Okay. So you say like the T1, the build up is the same as the relaxation time? The build up and the relaxation the other side. Okay.
Yes.
Okay.
And I mean, we have some cases where we see deviations from this, but this is because then nuclei start showing up that are not being enhanced. So, for instance, if we have how to say, like regions with agglomerates of paramagnetic centers, so these regions will relax very fast, and they will show up in the NMR spectrum, but they will have less contribution in the enhanced spectrum. And
I think you show the measurement that you did when you spin at 60 kilohertz, if I'm not mistaken.
Yeah. Okay. These are 60 kilohertz room temperature.
Yeah. And then like how would they?
Yes, you're right. Yeah. As we
And
go to
how would it
100
change if you go to like 10 kilohertz spinning, which is the case you use for DMP, right? So I'm just how would the spinning speed depend? How would this value change when you spin slower?
No, spinning speed dependence not at all, because the paramagnetic relaxation enhancement. So the relevant values are the nuclear alarm frequency. So and the correlation time is very short. So you would expect T2 to change if the correlation times become long, but this hasn't been the case for us. So the electron relaxation, or the T1e here, is still too short that the contributions of spinning, because basically the spectral density function at 0 frequency becomes the spectral density at the spinning speed frequency. But because the spinning speed is so short so small compared to T1e, we don't see any changes, and we don't see any changes in T2 with spinning, and T1 not at all.
Sure.
And with temperature, as we go down in temperature, we get longer and longer relaxation.
And because I'm just curious, like for these regimes, of course, like of course the lithium-6 spin diffusion does not play such a significant role here, right?
Yeah, correct. So,
but for lithium-7,
lithium-7
it will be different.
Are much shorter. Yeah, I mean, I can show you. Where is it? So we did all these T1 and T2 analysis also for lithium-7 and phosphorus 31, but there it's a little bit less clean because of the effects of spin diffusion. And
exactly.
But where is it? So here. So for lithium-7 and phosphorus 31, so we are what is it, like 2 orders of magnitude shorter relaxation time, something like that. But we still can observe the same trends. So there is a minimum of T1 and T2 as the correlation time of the electron relaxation changes.
Sure. Bob, I've asked my questions. Do you have questions?
Well, I'm just, I have a bunch of questions, but I noticed the time here. We're at 12:36 Boston time. So we've been on the air for an hour and a half or so, which is probably maximal time we should take. So I want to I think maybe we should truncate the presentation and the ZOOMinar today at this point. So I think we should thank both Daniel and Teresa for some really interesting new talks, very different topics and so forth, but really groundbreaking work in both areas. So again, Daniel, thank you very much. And Teresa, are you still there? I don't know. Maybe you've gotten lost with your 1 gigahertz machine.
No, I am. Can you hear me now?
We can hear you loud and clear. And so thank you. Thank you very much for a really nice presentation. And we'll be back here in 2 weeks from today, which is what's the date in 2 weeks, Kong? And who are speakers?
2nd of November.
2nd of November. Okay.
Yes.
Yes. I checked my calendar. It's the 2nd of November.
Mm-hmm.
And
right.
who are the speakers that day? We have them all lined up already? Huh?
Yes, we have them lined up, and in fact, you have already heard like this name appear like several times in Daniel's talk. In fact, so will be hosting Philip Gandinetti in 2 weeks later. That will be like the first speaker, and then like the second speaker will be Christian Dagan from ETH, who will probably tell us about NV centers.
Yeah. Okay.
Yeah.
All right.
Yeah,
Okay.
I just want to like remind you, like 2 weeks later, there will be this strange 1 week where there will be a daylight saving in one continent, but not in the other one. But so pay attention. So, but I will send out the email in the mailing list to remind you the actual time.
Okay. All right. Well, listen, again, thanks to both of you guys for really nice presentations. And we hope to see everybody back here in a couple of weeks or so. All right. Bye.
Thank you, Bob, for the invitation. Bye.
Bye.